Hello APC Mechanics students, in Unit 3 Work Energy and Power, Class 8 Conservation of Energy Part 2, Section 1 Simple Pendulum. A mass M known as the bob is suspended from a vertical string of length L and of negligible mass. The other end of the string is fixed to a support. Now basically this is the bob of mass M. L would be the length of the string that is connected to a support. The aim of this section is to study the dynamics of the system pendulum earth via energetic approach. Why our system consists of the pendulum earth in order to include the gravitational force in the mechanical energy as a gravitational potential energy. The equilibrium position of the bob is at point A. The bob is lifted to point B and released from rest. So we have lifted the bob to the left and we're gonna release it from rest, which means that the initial speed is 0. And by that it has no initial kinetic energy. Theta is the angle that the string makes with the vertical. A resistance is neglected, then the mechanical energy of the system consisting of the bob earth is conserved. This should be the bob. Now the energy at A is equal to the energy at B, where for E we're referring for the mechanical energy, and it consists of the sum of the kinetic and the potential. Here we're ignoring the elastic potential energy because we don't have springs. Now at the point, let me choose the PE level to be the lowest point in our system, which is the equilibrium position, and by that this makes the gravitational potential energy at A to be 0, and we have also the kinetic energy at B to be 0 because it's released from rest, and that would give us half V square is equal to GH, which is basically what we have derived previously, which is give us the impact speed in terms of the elevation h. Now the vertical height from the center of mass of the bob to the PE level can be expressed or written in terms of L and theta, as h is L into 1 minus cosine theta. Now basically here h would be the elevation, which is basically this, but we're interested in expressing this h in terms of the parameters of our system, which is given by the length of the string and the opening angle theta, and this can be done using simple trigonometry. Let me explain how. Now, so we're interested in determining this height, which is basically this portion here. Now all of that would represent the length of the string, and let me choose several points. Now this is the point A, this is the point B, and let me choose the point C. Now we're interested in determining h. Let me also say this is the point D. Basically h, which is the height from the center of mass of the bob to the PE level, can be written as AD, which is the distance from the point A to the point D, which is basically the distance CD minus CA. Now CD is given by the length of the string, and what about CA? CA for the triangle ABC, if we consider cosine theta, so this is a right triangle, then cosine theta is equal to the adjacent, which is basically CA, divided by the hypotenuse, which is L, which means that CA would be given by L multiplied by cosine theta. Then that would be L into cosine theta, and we can factor out L into 1 minus cosine theta. So basically the height from the center of mass of the bob to the PE level, which is chosen at the equilibrium position, in which theta is the angle with the vertical and L is the length of the string, is known as, or given by the following function, L into 1 minus cosine theta. So it's good to keep in mind this expression. How can you make sure that this expression is correct? By considering initial and final values. For example, if theta is 0, then the bob would coincide with the point A, and if you replace theta by 0, that would be 1, and 1 minus 1 would be 0, which means the height is 0. Now if theta is open at its most, which means 90 degrees, then the height would be the length L of the bob. So if it's here, length L of the string, so that would be the height, which is equal to L. And indeed, if you replace theta by pi by 2, which is 90 degrees, that would be 1 minus 0 multiplied by L, which is L. Now in this case, the speed, which is given by 2gh the square of the speed. Now we can replace h by into L into 1 minus cosine theta, and we consider the square root again. Then the speed of the bob as it passes through its equilibrium position is given by radical 2gl into 1 minus cosine theta, which is nothing but the impact speed that we know, and h is replaced by the theta function multiplied by L. And the maximum speed of the bob is attained at the equilibrium position at A, because the gravitational potential energy at A would be 0 and all of the mechanical energy is completely kinetic. For this reason, the maximum speed is attained at A. As the bob continues its motion to the other quarter, it will be elevated to a height at the point C with the vanishing speed Vc contained in the same slice of height point B. So in the first quarter, the bob moves from B to A, attaining a maximum speed at the point A. Then it will elevate to a point C. What I'm trying to say here is that C and B are at the same level simply because there is no dissipation of energy due to frictional forces. And this is anticipated due to conservation of mechanical energy. However, if the bob is released from B with an initial speed Vb, then the speed while passing through the equilibrium position at A is given by the square root of the 2gh plus v square b, in which h is given by the theta function. And we have added this term because we know that whenever we launch an object with an initial speed, the impact speed would be given by 2gh plus the initial speed to the power of 2, which represents the new maximum speed at the equilibrium position. As the bob continues its motion to the other quarter, it will be elevated to a height at a point D with a vanishing speed Vd contained in a slice of height higher than B. Now at point B, we have both kinetic and the gravitational potential energy. At point A, that's completely kinetic, and at the point D, that would be completely gravitational potential energy. For this reason, we expect that the point D compared to the point B would be at a higher height than B, and this can be anticipated easily. Why? Because if you're holding here a bob and give it an initial speed, for sure the new maximum height on the other quarter would be greater than that of B, and this can be done using the conservation of energy. Now, starting from rest at B, initially the system object Earth possesses a certain amount of gravitational potential energy Ug equal to the mechanical energy A of the system, which is represented by 4 blocks of energy. Now here in the following energy diagrams we're trying to represent the variation between Ug and K. The first column represents Ug, the second column represents K. Initially at the point A, at the point B, we have the initial speed to be 0. For this reason, we don't have any bars for the kinetic energy, and our energy is completely gravitational potential energy. For this reason, this has been represented by 4 bars. Now the number of bars is not important. During the downward motion of the bob toward the equilibrium position, there will be a complete conversion from Ug to K. As the objects start falling, the object will lose Ug and K in kinetic energy. Notice that if you compare the two, the number of bar diagrams is given by 4, which means energy is conserved. At the point in space Ug and K equalize. The equalization between Ug and K will be discussed later. And the kinetic energy remains to increase. At the PE level at A, which is the equilibrium position, Ug drops to 0 and is completely converted to kinetic energy, and the bob reaches its maximum speed. So that would represent the point A, or sorry, that would represent the point B, and that would represent the point A. Okay. Now, along the upward motion from A to C, the kinetic energy K will be completely again converted back to Ug, reaching the same elevation of A back again. Sorry, that would be of B back again. The same elevation of B. So that would represent the point A, and that would represent the point C. At the point A, it's completely kinetic. As we're going up, the bob starts to lose kinetic energy and it's gain potential energy gravitational, until at the point C it's completely gravitational potential energy. And if you compare all the energy diagrams that we have put so far, the mechanical energy is conserved and it's represented by 4 bars. Since there is no resistance frictional forces, then the mechanical energy of the system is always conserved. However, now starting at B with some initial speed, initially the system object Earth possesses certain amount of gravitational potential energy UG and kinetic energy K equal to the mechanical energy E of the system. So initially at the point B, we have gravitational potential energy and kinetic energy. Now it's not a reason why UG is greater than K. This is a matter of choice. We would have the case where K is greater than UG. This depends on the numerics of the exercise itself. During the downward motion of the bob toward the equilibrium position, there will be a complete conversion from UG to K. As the object starts falling, the object will lose UG and gain kinetic energy. At a point in space, UG will equalize. Then after that, toward the equilibrium position, UG will completely drop to 0 and K would attain its most, which is equal to the 4 energy bar diagrams that we have. Along the upward motion from A to D, the kinetic energy K will be completely again converted back to UG, reaching an elevation higher than that of A. So at the equilibrium position, we have 4 complete energy bar diagrams at A, and at a point in space going from the point A to the point D, they will equalize. And finally at the point D, it will be completely gravitational potential energy, and D will be elevated at a height greater than B, simply because at the point B we started our system with certain initial velocity. Since there is no resistance, frictional forces, then the mechanical energy of the system is conserved. Now section 2, horizontal oscillator. A block of mass m is attached to a Hookean spring of stiffness K and placed on a level surface of negligible friction. The other end of the spring is fixed to a support, thus forming a horizontal oscillator as that. Initially, the block is in equilibrium position. The block is shifted by an elongation x and left freely to oscillate. So basically at this point, the block will admit elastic potential energy. During oscillations, there will be a complete conversion between elastic potential energy US and kinetic energy K. The aim of this section is to derive an expression for the elongation x and the maximum speed v while passing through the equilibrium position. So basically, if this is the maximum elongation at this point, and if you release it from rest, the block will admit US maximum, which is the maximum elastic potential energy, and as it passes through the equilibrium position at this point, we don't have any elongation. The spring is neither compressed nor elongated. Then the kinetic energy K would be at its most. So at the point A, which represents the equilibrium position, in this case the speed will be maximum, and in this point, the point B, the elongation of the spring would be maximum. If there's no friction, we would expect that the oscillator will oscillate forever. Frictional forces are neglected, then the mechanical energy of the system oscillator Earth is conserved. So we have chosen 2 points A and B, and we're gonna say that the energy at A is equal to the energy at B. So at A we have 3 types of energies, at B we have 3 types of energies. We're gonna choose the PE level to be the horizontal level of oscillations or the center of mass of the block, and we can directly by that eliminate the gravitational potential energy for both points A and B, because we're not going up or down, we're staying in the same level. Now at the point B, we have released the block with no initial speed. For this reason, the kinetic energy at B would be 0. And moreover, at the point A, there will be no compression or elongation. For this reason, the elastic potential energy US at A would be 0. And we're left with half mv square is equal to half kx square. And here notice that the potential energy elastic that we have used for the spring is quadratic, simply because the spring that we're using is a Hookean spring, which is a linear spring. That means the force exerted by the spring is linear, and we know that the potential is the integral of the force, then it would be quadratic. Now we're left with mv square is equal to kx squared, then the speed through the equilibrium position, which is the maximum speed, and the elongation of the spring, and we say the amplitude of oscillations. The maximum elongation, so whenever we say elongation, we just mean any position while the spring is stretched. But whenever we say the amplitude of oscillations, that means the maximum elongation. Can be expressed in terms of each other, in which v is the square root of kx square over m, and x is the square root of mv square divided by k. So if you look carefully at this expression, suppose m and k are given. If we have the maximum elongation, this x is the x max. then the speed v square can be given by kx squared divided by m, which means that v is the square root of kx squared divided by m. Similarly, x can be written as the square root of mv squared divided by k. And notice that this is the case where m doesn't cancel, and it appears explicitly in our variables of motion v and x, simply because we have k, which basically doesn't cancel with m. So for this reason, springs are used as an instrument in order to measure the value of m, because they don't cancel with m. Now, starting at B from rest, initially the system oscillator Earth possesses elastic potential energy US, and it's equal to the mechanical energy E of the system. And this can be pictorially given by the energy diagrams. Now, we have three columns given by US, K, and UG. Because from our choice that the PE level will pass through the center of mass of the block, then all of these columns corresponding for UG will be empty, and we will be only filling US and K. Initially, we started from point B. The initial speed is 0, which means if this is B and that's A, at B we would expect that this would be empty, and all of our energy is possessed as elastic potential energy. Why? Because the spring is elongated. During the motion of the block toward the equilibrium position, there will be a complete conversion from elastic potential energy US to kinetic energy K. As the object starts to move toward the equilibrium position, it will lose elastic potential energy and gain kinetic energy. At a point along the motion, US and K equalize, and the equalization will be discussed later. At the equilibrium position at A, US drops to 0 and to 0 since the spring is neither elongated nor compressed, and E is completely converted to kinetic energy K, and the block reaches its maximum speed. Since there is no frictional forces, then the mechanical energy of the system is conserved. Now, exercise 1, a ball is thrown upward at a height of 10 meters above the ground. The ball has a potential energy of 50 joules and is moving upward with a kinetic energy of 50 joules with a potential energy equal to 0 at the ground level. So let's draw a figure, a diagram. This is the ground, and that's the PE level. Now, at a point in space, which is the point A, 10 meters from the ground, we have kinetic energy equal to 50 joules, and we have gravitational potential energy at A equals to 50 joules. They're telling us air friction is negligible, which means that we can use the conservation of energy at any point along the motion. The maximum height reached by the ball is most nearly. So notice that at the point A, both energies, they equalize. So the maximum height would be the double of this, which is 20 meters. Yet I didn't discuss this method, and this will be discussed later on. However, now let's suppose that we don't know this trick, and let's solve it from scratch. First of all, at the point A, because we know the height, we can directly determine the mass, because UGA is mgh, which is basically 50 joules. The mass would be given by 50, because all the numbers seems to be perfect. Let's use G to be 10. That would be 10 times H, which is 10. That would be 0.5 kilograms. So now we know our mass, and we know that the mechanical energy of the system is given by 100 joules, which is 50 plus 50. So at the maximum height, we expect that the mechanical energy, the sum, to be 100 joules. Let me say that B would be the maximum height, so the energy at B would be equal kinetic energy at B plus the gravitational energy at B. Because this is maximum height, the speed momentarily will be 0. That would be 0 plus mg h at B, which is 100 joules, and we're interested in determining HB. Then HB would be given by 100 divided by m times g, which is 100 divided by 0.5 times 10. That would be 100 over 5, and that would be 20 meters. And the correct answer in this case is B. Now exercise to a frictionless pendulum of length 3 meters with an amplitude of 10 degrees. At its maximum displacement, the potential energy of the pendulum is 10 joules. So at the maximum displacement, at max displacement, the energy is given by kinetic energy plus gravitational potential energy. We don't have elastic potential energy because you don't have springs. This is a pendulum. Now, because we are at the max displacement, the kinetic energy would be 0 because it will momentarily comes to rest. And that would be 0 plus the 10 joules which is given, which means that the total energy of our system is given by 10 joules. So at any moment in space, our system would emit a mechanical energy given by 10 joules, and there will be an internal conversion from kinetic to gravitational potential energy. So what is the kinetic energy of the pendulum when it is when its potential energy is 5? The sum should be always equals to 10. So if one of them is 5, the other would be 5, and the correct answer is B. Exercise 3, which is an exit ticket for today's video. A block of mass m is attached to a spring and placed on an inclined plane. The spring has a spring constant K, and there is negligible friction between the block and the inclined plane. Negligible friction, which means that we can always use the conservation of energy. The block is released from rest at the position shown in the figure above, with the spring initially unstretched. Then let me say that this is the point A. At the point A, the speed is 0 and there is no elongation nor compression. So basically at the point A, we would only have gravitational potential energy. What distance did the block slide down the plane before coming momentarily to rest? So let me say this is the point B under which the block will slide. Let me choose this to be the PE level. Remember that the PE level usually is chosen to be the lowest point in our system. We can choose it, for example, here, but it's more convenient to choose it at the point B in order to eliminate one of the gravitational potential energy. And now we're gonna say that, okay, remember that if this is a free response, we need to start by writing apply the conservation of energy and in this case we need to say that the energy at A is equal to the energy at B. Now the energy at the point A would be given by kinetic plus gravitational plus elastic, and the energy at the point B is given by kinetic plus gravitational plus elastic. Now at the point A we don't have speed, no, that would be 0. We don't have elongation or compression, that would be 0. Then it's only gravitational. At the point B it comes momentarily at rest, so the speed is 0, which means this is 0. It will be passing through the PE level, then that would be 0 as well. So we're left with the elastic potential energy. Now the gravitational potential energy is given by mg multiplied by h is equal to half k x squared. Now notice carefully here, h would be this distance. If this is the horizontal, then this is also the horizontal, then that would be theta and h. So sine theta is given by h over d, then h is given by d sine theta. So that would be mg d sine theta equals half k. Because x is the elongation of the spring, then in this case the elongation is given by d, so that would be d squared. This cancels with that, and 2 down becomes up and k's up becomes down. Then the distance d that the block slides is given by 2 mg sine theta divided by k, which makes d to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.